Welcome, ladies and gentlemen, to our AI and Space Robotics session as part of the ASITII Festival of Space, the Australian Space Industry Technology, Infrastructure and Investment. We have well over 40 speakers as part of the festival running throughout November from 4 different countries and across 17 plus sessions. My name is Chris Kottege. I'm the Executive Editor with MySecurity Media, and we're proud to produce this series of events for our spaceanddefence.io channel. Before we commence, I'd like to give an acknowledgement of country. In the spirit of reconciliation, MySecurity Media and our partners acknowledge the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander peoples today. And thank you very much for joining us. I'd also like to acknowledge the Festival of Space speakers. We, as I mentioned, well over 40 of them. So we are presenting a great body of knowledge throughout these sessions. And this is our second November session for today, as I mentioned, on space robotics and AI. Thank you very much to our sponsors. Our platinum sponsor is Inmarsat. We also have our gold sponsor, Fugro Spark. I mentioned our official media channel is our Space and Defence channel, so please check that out. And given that this is on robotics, we also have Drastic News, which is our drones and robotics channel as well, so please check that one out. And also we had our Women in Space series as part of our Global Space Week, and thank you to Lockheed Martin Australia that sponsored that session. So if our panelists can come on, and let me introduce our AI and Space Robotics panel for today. Navinda Kottege, who is the CSIRO Robotics and Autonomous Systems Group, Ali Buchberger, Director of Industry Engagement with QUT, Mohammed Bilal Shaikh, who is with our MySecurity Media and is also with Edith Cowan University, and Dr. Benjamin Kaebe with Space Industries in Perth. So we have representations from Perth, Queensland and Sydney. Panelists, very much thank you for joining us today. Quick mic check. For the audience, this is being recorded and you're very much welcome to say hello. Let us know where you're listening from. We've already got some from Brisbane and in Perth as well. And also welcome to fire in any questions that you may have during this particular session. AI and space robotics is a very broad topic, but naturally related. And this follows off in our National Space Capability session that we ran on Monday, looking at where Australia is. So I'm going to sort of start off with Navinda, and we did have Navinda on our MySecurity TV recently, looking at the DARPA Subterranean Challenge. Australia came second in that global challenge. So congratulations again, Navinda. And maybe what I'm going to get the panel to do is just introduce themselves briefly in terms of their roles with AI and space robotics, and then we'll get into a broader discussion on sort of the situation with Australia and our role with space in this domain. Navinda, there with the CSIRO, and congratulations again. I mean, you still must be getting the accolades from your recent win.
Thanks, Chris. So yes, I'm the group leader for CSIRO's Robotics and Autonomous Systems Group. We're based in Bullenville near Brisbane, and I'm also the principal investigator for our DARPA Subterranean Challenge team, which recently won second place in this Global Robotics Challenge, where we had to deploy a team of robots into various underground environments where we don't know about the environment. It's a harsh, unknown environment. It's no GPS and hardly any radio communication ability. And we believe that the technology and the capability that we've developed through this challenge has a lot of relevance to applications in space. And hopefully we'll be able to discuss more about that during today's panel.
Great, thank you. And to Ali, and maybe if I correct me on your name as well, is I try to say it with an accent and I didn't do very well. Buchberger?
Look, I offered you $50 before you got it right, Chris, and it's second time. I think you owe me, actually.
Yes. So your role with QUT as well, but Ali, welcome to Correct Me, Please.
Yeah, so no worries. Ali Buchberger. So I head up industry engagement for science and engineering at QUT. So we're an office of around 22 folk, so patent attorneys, business development people, government relations people, whose job it is to work with our really smart people, both at the university and within our ecosystem, to find solutions to industry's problems and get them out in the market.
Great. And to Benjamin there in Perth as well with Space Industries. Yeah, your role, and again, pre-session, we had a very broad discussion, but maybe your role with Space Industries and some of your outlooks and what the company's doing.
Yeah, so maybe quickly, my background is in AI engineering, and also I worked with Fugro Spark before, so I was very heavily involved in the whole development in Australia now with the remote operations and more AI for robots in space. Now I'm executive director for Space Industries. Space Industries is developing a lunar rover since 2018, and also more or less as a headquarter for ourselves, but also to involve more startups and other SMEs in Australia to help the ecosystem. We built the WA Space Precinct here in Perth, and that will have facilities to actually do the development and test and assemble the robots for space missions. Great.
And Bilal, they're at East County University in Perth, and Bilal does do some work with MySecurity Media on our automation as a data scientist. But Bilal, you're also doing research there with ECU, and your role with AI as well.
Yeah, I'm working in AI space around computer vision. So working around recognizing activities happening in different environments. So in AI, like there has been a great amount of like recent production in terms of new algorithms around computer vision, which can definitely help in space industries. And it comes to more about soft robotics, like in terms of simulating the space environment in a simulated environment. And this is where I see recently, like the recent advancement in AI has increased the accuracy and precision of those soft environments. And this is definitely where we can mock the space environments in the soft robotics environment. So my work is more around computer vision and understanding images. And with ECU, I'm the member with the Governance Council, and I'm doing some video analytics and AI with MySecurity Media, and looking ahead to learn from the panel. Yeah.
Yeah, and look, we are all here to learn from all of you. I think one of the things I wanted to cover off on, and Ali and I briefly discussed it yesterday, is the key differences between an Earth robot and a space robot, and why they are so different. Navinda, I might start with you, and because it's obviously a communications issue, and I think it does bring us back to the DARPA Subterranean Challenge. So anyone who's not aware is definitely worth having a look at that particular challenge, and how you would relate the two, subterranean to space, and some of the sort of the commonalities and differences. And then Ali, I think I'll come back to you in terms of what research and work that QUT is doing.
Yeah, thanks, Chris. The DARPA Subterranean Challenge and the task that we had to do in that has relevance on multiple levels to applications in space. The most obvious one is currently scientists are looking at potential habitats for humans in planets like Mars, for example, and even on Luna. The main focus had been on subterranean lava tubes as potential habitats for humans, because that shields you from some of the very harsh temperature differences and the solar radiation that you have to deal with. So the technology that we developed here for the Subterranean Challenge directly addresses going into subterranean environments such as natural caves and man-made tunnels underground, and how do you deal with this type of harsh environments where you don't have your usual GPS-based localization, you don't have communication to your fleet of robots that go exploring into this environment. So that would be kind of the direct relationship, and then beyond that, you mentioned communication, which is really very relevant topic, because even in our DARPA Subterranean Challenge, given the harshness of the environment, there was no guarantee that the human supervisor at the base station would have radio connectivity to any of the robots that are sent into this environment. And even if we do have radio connectivity, it'll be on a very low bandwidth and latent channel, which has latency. And this is amplified to in several orders of magnitude when you talk about space operations and remote operations in space, whether it's lunar or even Mars, where the round trip delay can at maximum be around 20 minutes. And this is not feasible for you to do remote operations, as in being able to have a joystick to control a robot from Earth. And that's where autonomy really comes into play, and that's something that we've focused on in our technology development, where you give sufficient level of autonomy for the robot so that they can still perform useful operations with high level human supervision. So in a Mars context, for example, if we have a fleet of robots there, and if we only have a human operating it from Earth, it'll be a matter of getting all the sensory information through and sending a high-level mission goal or high-level command that allows the fleet of robots to go and do something useful, go on exploration task, and the robots themselves to have enough sensory and autonomy capability to successfully complete the mission, give the humans useful information back. So that would be one of the things where the level of autonomy that we've developed would become relevant in a space context.
Great. And Ali, the work that QUT is doing on transition, you pointed out, what are the key points that you would raise in terms of the difference if someone's building a robot here on Earth and thinking, oh, this might work in space? What are those key sort of points that you would raise immediately? And then some of the research that you might be doing in this area, is it research rich in terms of the work that is yet needed to be done?
Look, I think it's research and commercially rich, to be honest. I think there's enough commonality that there's a really convincing case that Australia has a competitive advantage in terms of being able to leverage our really robust sort of field robotics and automation capability, which we've developed through our resources sector, to have a competitive advantage in space. You know, robots, I think as Navinda was saying, robots belong where people don't. Where it's really expensive to put people, and astronauts are really expensive people, or where it's unsafe. And I think this is, however, where the difference is. The lunar surface, for example, is not just unsafe, it's inhospitable. And so I think when you're developing a mission, you're guided A, by the mission objective, but B, by the environment in which that mission takes place. So in terms of the lunar environment, we're talking about a 6th gravity of Earth. We're talking about an exosphere rather than an atmosphere. So light conditions are completely different. And this impacts how a robot will navigate, perceive, and move. Temperature variations, huge impacts for the materials you choose. So, you know, you're talking about sort of 127 in the lunar day down to minus 173 for the lunar night. Surviving the lunar night is a really, really big challenge. Dust, highly reactive dust that sticks to everything, gets in your electronics, you know, clouds your sensors and your cameras. It's really difficult for a sort of rover to navigate in those conditions. Radiation 200 times what it is here on Earth affects, you know, electronics, communications and everything. Energy, there's no energy in space. Comms, there's no comms in space. You know, the more you add in size and weight to increase performance, the more it costs. And so a lot of trade-offs to consider.
Thank you. And I was expecting you to keep going. Is there any, like, there's enough?
You wanted me to talk about a QT project, so I will, and it's not a rover project. It's a project we're partnering on with Canadian Space Prime MDA. And it was based on our observation of the International Space Station, which obviously will be decommissioned, and we're going to build the Lunar Gateway. The ISS is a complete logistical disaster. It's just full of decades of stuff.
End of life.
I mean, it looks like, you know, your teenager's bedroom on its best day. Let's put it that way. And from what I understand, talking to astronauts, a lot of the comms link time down to Earth is not spent sort of talking about how to do this important experiment. It's about where did someone put the toothpaste. And so given Gateway is going to be uncrewed 90% of the time with even more limited comms links down to Earth, finding a robotic logistics solution is going to be really, really important.
Great.
So we've spent a lot of commercial effort trying to get cargo to space stations, you know, through MDA and others around those sort of external robotic systems, but no one has yet taken care of the internal logistics. And so that's what we're proposing to do. Nice.
And Benjamin, you mentioned something pre-session, was if you design a robot for space, then you can deploy it in almost any environment after that. And as Ali pointed out, there was so many different things that you have to contend with. It does sound like Northern Western Australia, the way she described it. In some of those environments.
It's even worse. I mean, yes, in Pilbara, for example, we have also a lot of dust problems, and the dust also gets everywhere. But to add, I mean, obviously, all the points Ali and Navinda have mentioned are completely true, and it gets even worse if you then consider with the dust, for example, it's also electrostatically charged, so it flies because of the low gravity. It's so like a plume, and then sticks to your surface. So and then if you have, for example, as an energy source, a solar panel or something like that, it will also cover the solar panel and hence reduce the efficiency of the energy, of the scarce energy you already have, even less. What I pointed out before was when you develop a robot which can survive the harsh environment in space, then making that robot working on Earth is way easier, because you can take actually things away. You don't have to have the radiation shield, you don't have to use the same material, and so on. The software is also like when you solve that latency return trip time to Mars, by the way, it's one trip is 20 minutes in the worst constellation. So return trip is actually 40 minutes. So when you see something on the screen and you react, it actually takes 40 minutes before the robot can also react. But if you solve that problem, suddenly you can enable drone remote operations, right? And but then there's another sort of hurdle as well, like a part of all these harsh environments and so on, but even the mission control and the mission operation is different. How is the robot, let's say we do on-orbit manufacturing or on-orbit maintenance, if you attach to another satellite with a robot, then suddenly you have to consider two bodies, and every movement of an arm will impose like a complete change of the orientation of your satellite as well. So suddenly you have a multiple system, multiple dimensions you have to actually sort of also tackle before you can actually do something. So all these things have so many spin-offs automatically into other areas, because it's very, very complex to do that in space. It's not that easy.
And welcome to our guest in the US, who's just raised something, and I was going to bring it back to you, Benjamin, but we'll go to Bilal first on the vision. But there's a question here on the commercialization in Australia, so we will get to that. Thanks, Tenzin, from the US. And where in the US are you listening from, out of interest? But Bilal, the vision, you talked about AI and vision research, and then Ali raised, and the panelists raised in terms of dust, the lighting is different. How advanced would you say our vision and video analytics is at the moment, in terms of then, you know, because we're still struggling to get the driverless cars and a few of the others that require that vision analytics. How advanced would you see that is? And, you know, do you think it's adaptable, so to speak?
I think adding to what Navinda was talking about, like there are challenges around deploying AI in robots as well. Like one sort of like a perspective is around communication, so that we are not sure still like what will be the communication when the robots are on Mars or Moon, what will be. So and with vision, the vision models are normally very heavy, as like if you deploy them on, and normally you see vision models for self-driving vehicles like you name it, like Tesla. They have very heavy vision models, and they are normally like they require huge compute power. So one potential option there becomes for AI robots in space is the edge computing that's coming in. So a lot of models could be deployed on the robot itself, and it can do a lot of it can make a lot of high level decisions, as Navinda put it, in the space environment. And then after making a lot of subsequent decisions, the robot can come up with something meaningful out of its environment, and whenever the communication happens from our end. One certain example is that another thing where AI is very contributive is the simulation of the planetary space environment, because recently I have seen a lot of precision and advancement in the deep learning space, which has developed some simulations which are high in precision if you go to 3 to 4 decades ago. So that's a very recent advancement. So what we can do, which is already happening, I see, is that soft robotics, like it's an all soft space environment that is visually physically simulated, and so you can think about all physical aspects of it, dust or whatever environmental changes coming in. So you can already answer those obstacles to the robots in a soft robotics environment. This is where I think, and where there you can use the offline compute power as well, which is not the fact if you do that on the edge. But recently there are some chips that are very powerful in terms of deploying those vision models, but they are still not all up to that level that we cannot deploy all self-driving vehicle models on those edge computing devices for robots. So there are a lot of challenges around it, but the way AI is answering a lot of questions at the moment, and I think it's a very important contributor to the exploration in space now. Yeah, definitely.
And Navinda, maybe back to you in terms of the work that you did with the subterranean challenge, because obviously that's something that you would send sort of that vision robot out there to map and create that visual model of the environment. Then you can send all that back to Earth, analyze it, and then create missions within that new 3D model that you might have created. Is that one, I know it's simplistic, but is that potentially one way that we would be looking at deploying robotics into space?
First of all, in our case, our main modality of sensing was necessarily vision. We did use vision for detecting various objects, but we were mainly using LiDAR. But that again is yet another sensing modality, and we used LiDAR is using scanning infrared laser where you collect information about your environment, and we were using a technique called SLAM, or simultaneous localization mapping, to develop a 3D map of the environment that's around you. And to me, what's important is kind of going beyond the sensing modality, but focusing on what we refer to as situational awareness, so that robots in a remote environment, such as a planetary environment, can use vision-based sensors or LiDAR-based sensors to give enough situational awareness and give that intelligence back to the human operator, whether they are in a habitat on the planet, or if they're on an orbital spacecraft, or if they're back on Earth. For you to be effective in your decision making and your judgment, you really need to have as much situational awareness as you possibly can need. And I think that's where additional techniques that Bilal mentioned, things like edge computing and machine learning based techniques really help, because in reality, just having, let's say, 10 camera streams is not necessarily giving you good situational awareness, because you need that processed information, and it's a research area of its own. Like, how do you kind of distill these many streams of raw information that can be presented in a useful manner to the human operator?
Go Benjamin on that, and then Ali, I'll come to you.
Yeah, so two things which is extremely important to note here as well. Yes, you need on-the-edge computing to do a certain task because of the delay. Yes, you need more sensing or more situational awareness, but just to emphasize how hard these things in space are, now we run into the limitations of, okay, how much edge computing can we take with us? How much sensors can we take with us? How much energy do we have available? So, but the chance here is once we solve that, we can, for example, manage way better how much data, for example, are we sending back to Earth? So how can the computer on the edge optimize the amount of SLAM environment data, for example, being sent back, so that not all 1 trillion pixels are being sent back at all times in real time, but sort of in a packaged way, or sort of collects the information once and then sort of identifies with machine vision certain objects, and only a vector, which is then six numbers, are being sent back to reduce that amount. But again, you need to think of, okay, how can I achieve that with a very minimized battery power, with a very minimized amount of CPUs I can bring with myself into this environment, and even what kind of CPUs are available for high PC tasks in a radiation hardened environment, of like when you need radiation hardening. So I think that's very, very important to note.
I think the key outcome here is there's so many different considerations that you need, and each is interdependent on each other and interrelated as well. Ali, given your role with QUT as well, I like this question from Tenzin, who's in Pittsburgh, but originally from Adelaide, so you count still as an Australian, I think. I noticed there are a lot of panelists from research today. I would be really interested to hear everyone's perspective on space research commercialisation in Australia, what's working, what's not, and any major challenges compared to other space nations. You pointed out you have a range of different sort of commercialisation programs. What would be some of the sort of the highlights, other than the ISS program as well, but some of the research that you see coming through that has commercialisation opportunities, or even some that have been successfully commercialised?
Yeah, sure. Yeah, and thank you to Tenzin. It's a great question. Look, I think a lot of the great space tech that's being developed is coming out of universities, but in partnership with industry. And I think one of the successes of the Space Agency and the federal government is really to encourage those collaborations through the funding programs that they've established. So Modern Manufacturing Initiative, and obviously the Moon to Mars program through the Space Agency. I think, I mean, there's two ways you can commercialize. One is through licensing arrangements, and the other is through, in terms of sort of university commercialization, the other is through spin-out companies. And I think there's potential for both. I think around licensing, there's always sort of challenging negotiations around IP. And I think, the parties just need to think through in those situations, do we actually need to own the IP? Do we only need to use it? What do we need to use it for? Is it for every industry? Is it for everything within those industries? Is it just for space, or is it in a subsector in space? Do we also want to use it for defense? Do we actually need to use it for agriculture? Is it for military or civilian purposes? And on that basis, reach an agreement, because nobody wants to see intellectual property sitting within a university. We all want to get it out there. It's only useful if it gets out of universities.
Is that part of the challenge? Is that part of the challenge of it has so many different opportunities? It's almost too many, and you've just got to go with your best one. Therefore, as you say, it could be sitting there idle if it's not being used across the board. Mm-hmm. Is that a challenge in itself?
Look, it's always a process to go through to understand the technology, how it can be used by whom. and find the best solution. It's like any technical discipline in a way to go through that. I think with spin out companies, maybe just a quick comment on that. I guess when you look at those two commercialization options, typically licensing is used when there's an opportunity in the market right now. Whereas a spin out company is a great vehicle if you're looking at a commercial opportunity over a 10-year time horizon, which is a really comfortable time horizon in the space industry. They're the timelines we work to all the time. I think the challenge though for Australian startups is, again, you know, acknowledging there is, you know, high risk, high return in that kind of scenario in space, but how can we generate sort of more assured near-term returns in the terrestrial market? So I think the companies that will succeed are those that can create dual-use technologies that deliver both for investors.
That definitely came out of Monday's session as well. Dual use was a key term, and also we need to increase their speed, but also be prepared to fail faster. I'm going to come to Benjamin on that as well, and I see the panelists are all able to come in. But Benjamin, space industries and where you're at, because again, you want to create a hub over in Perth. You know, raising money again slows it down. The traditional way of raising money and proceeding might not be at the right pace. How are you sort of dealing with the commercialization challenge, I suppose, across what you're doing?
So first of all, the question is not just good. That's the key question we have here in Australia at the moment. I think what's going wrong currently is that more big companies get funded by the bigger grants, and a lot of startups are not really getting traction, and that should change. I do completely agree that anything you develop for space has to have spin-offs on Earth. Otherwise, you cannot convince investors to be interested in what you're doing. And you also need to find a way to protect your IP for space use, if that is what you really want to do, but then license it out or sell it for terrestrial use. And that could be a pathway to then fund your projects via this via this way. So we are with Space Industries, we're developing a lunar rover, which will provide NASA Artemis, or can provide NASA Artemis with water, which is in high demand on the moon. A liter of water would cost $30,000 to send it up there, and we can provide it for a tenth of that amount. And that is sort of our long-term goal for that commercialization. However, all the sub-technologies for that rover itself have terrestrial applications. We are now in negotiations with big mining companies around the world who are interested to build a pilot plant with a mining process we've developed. The robot itself we're developing will have terrestrial use for agriculture. It can also extract water from sand, and therefore has huge potential for agriculture. It can be remotely operated to do exploration in harsh environments as well, and so on. And there's a number of other technologies. And the first thing, and now coming back to the startups where that is so important, what we are building is a precinct at Perth Airport, and we want to involve a lot of startups and bring common facilities to them so they don't have to pay this overhead. So we will have the largest clean room in the Southern Hemisphere, for example. So people who are on the precinct can use that. We will have a mission control center. People who are on the precinct can use that. Engineering offices with computer-aided design and so on. So that's all like to reduce the overhead costs to actually build a community with startups and SMEs.
Well, I think when you talk about hubs like that, I think that creates, even if we have in Australia, create a sense of competition as well here will assist. Navinda, I don't know which way you want, but obviously the CSIRO have had a number of commercial spin-outs as well. But yeah, over to you in this context.
Yeah, so I think before I address that question, I'll bring in some terminology which I'm sure most of the panelists might be familiar with, but for the benefit of those who don't, it's this TRL levels, or the technology readiness levels, and I think that's very important to kind of understand. This is terminology used by NASA and the US Department of Defense. So it's so the technology readiness level goes from 1 to 9. TRL, I'm not sure whether it starts from 0, but I think 1 is basically kind of idea on the back of a napkin type of thing, and TRL 9 is something that can fly to the moon. So it's not a linear scale; it's a very exponential scale, and typically universities operate in maybe up to TRL 3, 4 type of level, and organizations like CSIRO, we typically don't operate in the very low TRL levels. In some cases we do, but we tend to go up to maybe TRL 6, 7 in some cases, but we don't go beyond that, because the reason is the amount of resources and engineering that's required to go from, let's say, TRL 7 to 8 or 8 to 9 is massive, and a lot of people don't understand and appreciate that. And I think that's a key component in this whole commercialization piece, and then being able to be competitive in that space as well. So having something that you can demonstrate in a representative environment is good, but that doesn't mean it can be sent to space. So on that note, CSIRO does have multiple models of, I guess, getting the IP out of the door, because we do develop a lot of very interesting IP, and in some cases it's a licensing model, some cases it's setting up a joint venture with another company, or even spinning out companies ourselves, and that's something that we have done. Even my lab in the past few years, we have spun out companies. But I agree with what Ben said. I think sometimes it's useful to have funding models that favor some of the smaller agile startups, because sometimes they actually can move a lot quicker than some of the bigger players. And I know we can't call them a small company anymore, but SpaceX was a great example a number of years ago, because it was an area that was dominated by very large players, and then they managed to come in and really disrupt the whole industry. So I'm sure that there's potential for many more of those in the space domain.
Well, it's also the speed. So Bilal, in terms of the speed of developments and from that commercialization opportunities, what's your observations in that as well as here in Australia in terms of the support for startups in this space?
Yes, I think I've been into a lot of interactions with the mining companies, and Australia has this edge. Like a lot of mining companies have experience about remote operations, and they have been internally developing a lot of efficient AI and exploration capabilities. If this gets integrated well with the research happening at universities, I think that will be an edge factor. And as Navinda and Ben talked about the IP commercialization, I think there is a lot of effort required in that space, because it's not an independent space here in Australia that new startups can jump in. It's a pretty experienced space to if someone wants to disrupt this industry. So I think yeah, a lot of things are happening in different research hubs around WA specifically, I would call. And I have seen a lot of this is the mining sector is a bit of edge factor when it comes to space industries for Australia, because it enables you a lot of prepaid ready-made aspects of your develelopment, I think.
Yep. I think mining and agriculture is obviously two strengths and core industries for Australia that are sort of crying out for innovation as well. But mining, you know, particularly there, if, for the international audience, if you're not aware, you know, a lot of the mining operations in northern Western Australia are remotely operated from Perth, driverless trucks and the like, driverless trains. And there has been a couple of comments also in terms of agreeing with the panel in terms of maybe a lack of support for startups or going to larger companies, particularly American companies. There's a question here from Rajen. What are the research collaboration and opportunities to develop technology with the CSIRO for particular application in mining sectors for startups in Australia? I might come to Ali if you don't mind. Ali, what's your observations in Queensland? Because Queensland's obviously another strong mining state. Is it, you see much collaboration within this domain of AI and robotics? Potentially, we can bring in drones a little bit as well with the industry, with industries such as mining.
Yeah, look, I think, you know, the mining industry is changing. There's a huge focus for most mining companies on sustainability, but also an increasing appetite for disruptive technologies. I think, you know, mining on the moon is a bit of a misnomer. You know, Rio Tinto, I don't think is going to mine on the moon anytime soon for a whole range of reasons. But I think what is of interest to mining companies are those technologies, you know, energy assets, solar arrays, electrolyzer technology that can provide energy infrastructure on the moon. You know, the robotics and automation technology that can help them mine more precisely and more efficiently and more sustainably. And those are the kinds of technologies that will completely disrupt mining here on Earth. And, you know, if it's sort of space mining companies that develop or acquire those technologies, you know, they'll become, you know, the Uber to sort of large traditional mining houses here on Earth. And that's a huge risk, I think, for those operations.
I might even open up to that particular discussion, Navinda, from your experience looking at the work that you did with DARPA. Is that where you envisage this going? And also looking at the environmental challenge that we have here on Earth with mining, is mining in space where we are potentially headed? And do you see it as ever actually getting there?
Look, I think a slightly different perspective on that. I think something that myself and our colleagues here at CSIRO have been focusing on something called ISRU, or In Situ Resource Utilization. And that's a little bit different from mining in a traditional sense. It's more about addressing the problem of the cost and the logistical difficulty of taking things from Earth up into space. Because if you need to build something, if you want to even sustain your mission, you actually need to utilize resources that are already there, rather than taking everything from Earth. So that does require a certain level of expertise or learnings that we can get from this traditional mining type operations, but I wouldn't necessarily see that as just as Ali said, kind of commercial mining operations on the moon or on Mars. So that's kind of the focus that we've had. Like, how do we operationalize that? How do we learn lessons from what we've done here on Earth, and to do that? And it, as it was mentioned by Ben and Ali earlier, a lot of people, even including myself, until a few years ago, I didn't fully realize the harshness of some of these environments. Like we are working with our colleagues here in setting up a lunar analog environment here to test some of our robotics technology, and the analog to lunar regolith is made out of crushed glass and asbestos, so it's that bad. So one of the anecdotes that I heard was the only thing that doesn't stick to lunar dust is lunar dust. So there was even a suggestion maybe we should coat everything with lunar dust to stop lunar dust from sticking to it, type of thing. But yeah, so these are the challenges that we are trying to I guess address in the coming years. Simple things like you can't have rubber in space.
Yeah.
So you can't have rubber tires on a rover. So these are things that a lot of people here on Earth just take for granted, and it's just not there for you to use out in space. So there are lots of engineering challenges that you need to solve, and the learnings from the DARPA project that we hope would translate into this environment is not necessarily the building space hardened robots. I think that seems to be in Ben's code. What we are trying to do is more from the autonomy side of it, the software and kind of a systems approach. How do you deal with a fleet of robots? Because for us, going into an environment, it makes a lot of sense to have a fleet of robots rather than just a single robot. For for redundancy as well as for area coverage and the efficiency that it brings. So how do you deal with a fleet of robots? How do you do multi-robot navigation in a harsh environment? The environment itself is harsh from a mobility point of view, but also from a sensing point of view, processing point of view. So one of the aspects that we had to deal with in the DARPA challenge is called austere navigation. So where you don't have as much resources as you want in terms of your power budget, your processing budget, and all of that. And these are amplified in orders of magnitude when it goes to when it comes to space, as Ben mentioned. So
you got additional points for those as well on how you dealt with them, didn't you?
Yes. So the challenge was set up in such a way that it rewarded teams that actually did address those problems. So yeah, we absolutely take so many things for granted here on Earth, which just is not simply available in space. So so from a software point of view, from a navigation point of view, from an AI point of view, there are so many challenges that we need to solve. But I think we are kind of getting there. Like the solutions that we've come up with in multi-robot navigation in unknown environments has applications in that area. So we are focusing more on how do you get your assets to interesting places, and then I guess there'll be other technology providers who kind of come in with all the other value adds on top of that, where you can do. Yeah, I wouldn't necessarily say off the shelf, but I think there are technologies that needs to be developed in parallel to efficiently do energy harvesting and then to do in situ resource utilization and things like that.
Right. And Benjamin, your domain in this as well, and even if you want to bring in some comments on your thoughts on the Artemis deal as well, and but how you're addressing the challenges.
Yes. Well, so first of all, I love this here. It's a really cool panel. I constantly want to jump in because there's like so many topics. I could add something, and I guess I think my co-panelists are having the same feeling. Anyway, I wanted to add one thing to space mining. Space mining it's completely different to what we consider mining here on Earth. It's not like we're digging up a lot of things and then like sort of bring all the iron here and then bring it back to Earth. In fact, it would be stupid to find an asteroid made of gold, bring it back to Earth, because a lot of people forget the economy factor here. If you bring such a big, let's say you bring an asteroid back, you invest like $300 million, bring an asteroid back to Earth, which is like 5 times the amount of gold you have in Fort Knox. So what happens with the gold price now? So gold is worth nothing anymore. So you bring that back, you have invested so much money and you can't really sell it here anymore. So that is not working, right? And the same things, obviously, with the space treaty, we are not really allowed to sort of damage planetary or celestial bodies. And therefore, whatever we do has to be very, very friendly to that environment. And also, just a side note, just to show how harsh the environment on the moon is. So they suspect water ice in the permanent shaded craters, for example. Just to go there, there's no sunlight, so there's no energy. To get down there, it's very, like the slope is actually very, very steep as well. It's 4 Kelvin, that's minus 285 degrees Celsius, something like that. So it's like the most harshest environment you can find in the universe. And you have nobody there. So there's nobody there who can help like lowering the robot. So these things like require a lot of thinking and to tackle that. But coming back to your question, so our goal is, as I said, we want to provide NASA Artemis with water. So they will need that for propulsion mainly, and also for energy, water to drink, and for oxygen to breathe. But I think the main thing will be propulsion. So a lot of people don't realize that the moon, being like the closest celestial body we have, actually bears the capability to launch from the moon to Mars. If you launch something from Earth, there's the rocket equation: 90% of your fuel, regardless how big or small you make your rocket, 90% will be used just to leave orbit. That means you have only 10% of your capacity to reach wherever you want to go now. If you can refuel on the moon with water, and water is with electrolyzers, obviously water is oxygen and hydrogen, which is a propulsion, you can then go from there to Mars. And therefore the moon bears that opportunity to become a refueling station. And then obviously you don't want to bring the water from Earth, because if you have it there, then you have the advantage actually to use it there and then go further, and then you reduce the logistic cost. And that's what space mining is really about. There are, on the other hand, there are elements which are available on the moon, which we don't have available on Earth, such as helium-3, which actually has the potential to be economically viable to be used on Earth for fusion, for medical applications and neutron detection and so on. But there are things, but it's not like we build a big mine pit and bring like lots of stuff here. So it's completely different. I think that is something we have to recognize here as well.
I think what I might do is, just conscious of time, and as you say, it is a big topic. If we could just bring you back maybe to the strategic space pillars, there's 8 of them, and maybe where you see Australia being quite strong in the domains and where the real opportunities are, but also any regional opportunities as well, not just for Australia. Something was raised the other day in terms of the Quad with Japan and India. And then also we've got AUKUS, Australia and UK and the US, where you kind of see our key strengths and regional cooperation as well. And Bilal, particularly where they're in the research that you're doing in the vision, how much collaboration are you seeing either between universities and researchers, but commercial applications in terms of the advanced research and any sort of more regional collaborations that you're observing?
Yeah, I think particularly around this vision space, I have seen a lot of startups doing solving these problems, but I see regarding the real life application, I think they are a bit more hesitant towards using the recent advancements happening in research. It's not very lively applicable there. I have seen certain scenarios of deploying these vision research models. So it takes, I think there is a sort of a gap that is happening in research and in the industry. So it's I have seen a lot of different startups that are using traditional approaches as compared to more recent AI models to recognize events happening in prisons or in surveillance environments. So they are using something that is working very much. But another problem with AI is that's happening in research is it's not explainable. A lot of AI models are not explainable. So like the traditional machine learning used to be very like as required. It needs to be explained till at what conditions it's making a decision. But recent deep learning models with AI and where vision is mostly based on deep learning models, and it has the accuracy has so much increased. So this is a challenge that startups or industries are facing in deploying these AI models, that they are not explainable. Sometimes if they are wrong against adversarial facts, let's say something like the situation changes. So I think that's a bit of a challenge, and so it's happening a lot in the research space, but it's not live. As we can see in self-driving vehicles, they cannot say that 99% of the time our vehicle is safe. No, it's not. It's one scenario can.
Yeah, I think that's called the black box of AI, isn't it? Where you don't know how it's making its decision. And we've also then got the ethics involved in that. And as you mentioned, a lot of what we're dealing with obviously is with humans in that scenario, and we're trying to learn what humans are doing. Whereas in space, that's not going to be the scenario. We've got a couple here, human presence becoming a reality on the moon anytime soon. I think it will do, I hope so. But maybe closing comments from Benjamin as well, where you see this all heading, maybe the outlook and expectations for you at Space Industries and the broader sort of space industry. It's an international industry, and where you sit in it there in Western Australia.
I believe that Australia needs sovereign primes to license out like terrestrial applications and IP. I do think that Australia has to back up more startups, and then I see a really good future for us. I think with space, and I mentioned that in the pre-session as well, space for me means communication, AI, robotics, remote operation. And remote operation itself is also not just the tech, It's also, how do you plan a mission? How do you operate? And that's where we have actually a lot of expertise. And cybersecurity is obviously as well one of the pillars. And these things have by themselves a huge impact worldwide. And we can actually lead the world in these fields.
Very good. And Ali, I suppose that's part of the challenge, even for a university, but for anyone in this area, is focusing, because I have FOMO at best of times, and trying to focus on something. How do you grapple with that? And yeah, your sort of outlook and expectations to sort of close off here.
Yeah, join the FOMO club, Chris. That's all I have to say about that. Look, I thought I'd finish maybe with a comment around talent pipeline coming from a university in relation to those civil space priority areas. Yes, we will achieve industry growth in all of those areas. Yes, we will create jobs in all of those areas. We need skilled workers to fill those jobs. We all know we need more engineers. We all focus a lot on, STEM education. Space is about more than just that. We need people to run space companies. We need space lawyers. We need commercialization folk. There's a whole range of skills. It's encouraging to see universities creating space degrees now, or embedding space across a whole range of relevant disciplines, from materials to data to energy to mechatronics. So I think it's also encouraging to see, great internship programs and talent sort of pathways into industry and companies like Boeing. In 5 years' time, I would love our best mechatronics engineers to be staying here and working for a company that makes Australian rovers and not going to Google DeepMind.
Very good. I think that's part of the challenge here, is that skills. I'm glad you mentioned the skills. Thank you. It's on my list here, but also keeping them here in Australia and not necessarily losing them. And I think the same thing will be said about startups, making sure even if we do develop our startups, that they stay here and the successful ones don't leave as well. Navinda, you're really in the box seat there in this domain. Your outlook and expectations over the next few years. DARPA Subterranean Challenge took 3 years for a start. So yeah, what's your kind of focus over the next sort of 3 to 5 years, and where you'd like to see things going?
Yes, so our focus right now is translating the technology and the capability that we've developed into real world use cases, and this could very well include activities in the space domain as well, but even on the terrestrial domains, there are so many use cases and industry segments that we can apply our technology. So that's definitely one of the focus areas. And space is something that's quite exciting, and operations on space, it's definitely an upcoming area with a lot of activity here, even in Australia. It's natural for us to kind of compare ourselves against the US, I suppose, but compared to the US, yes, funding opportunities are probably lower here in Australia. I'm hoping that will change with time, but as Ben mentioned, we have a wealth of knowledge and experience from mining related remote operations. I think we're way ahead of the curve in the world when it comes to that sort of technology, and that has a lot of application and relevance to space operations. And I'm hoping that can actually translate into that, and then we are happy to kind of work with other partners to help realize that through our technology as well.
It did raise, there's a question here from James on the bridging that gap between, so NASA and other space experience companies. America's been referred to as well. Do you think when you hear agreements like AUKUS, that is a good thing, or the Quad in terms of India as well, and Japan? Do you think Australia will need to have regional partners and our global partners? Do you think we're partnering enough in that context? Maybe to Ali, do you find that there's enough collaboration internationally, or are we still doing it ourselves singularly?
Look, it's obviously a key objective for the agency. The announcement of the first Australian moon mission in collaboration with NASA is obviously a huge step. I find our space industry to be highly collaborative, but we are a startup industry here in Australia. And so I think given that we're growing so quickly, the next big challenge for our startups here in Australia is going to be to break that glass ceiling and to compete competitive, to secure a competitive advantage in global markets. And that's going to be, a big challenge over the next 5 years, I think.
Well, I think just to close off, and we've gone full time, and I think we will close it off, but some of the observations we've made, it's very similar in a way to, say, the startups in the cybersecurity sector as well, getting that VC funding, the commercialization opportunities here in Australia before heading off to, say, markets like the US. And some of the key terms we didn't quite touch on is, say, AI accelerated design, AI automated testing, and we did look at the synthetic data, the 3D models of AI as well that are there. It's a big topic. We covered off as best as we could within the hour. And if you let me, I'm just going to bring up our panel slides again as we close off. We should see that. So thank you so much to our panel today. And if you've got any other comments or questions, fire them in now and we'll see. But otherwise, you're very much welcome to reach out to the panelists directly as well. There is some collaboration opportunities there, no doubt. So thank you, and I'm going to try this panel, these names again. We've all got the best names individually, but Ali Buchberger.
Still not there, Chris.
Just for the audience listening, tell us so I get it right, and I'm going to practice.
Ali Buchberger. Thank you,
Buchberger. It's the Buchberger. Benjamin Kaebe and Navinda Kottege. Beautiful. And Bilal Shaikh. And my name is Chris Kaebe, for those who also have problems with that. Thank you so much to the panel today. Great inputs, and we do hope to have you back. Just for the audience, ASITII is an ongoing festival. We will be throughout November, but we're going to be continuing into 2022 as well for this. And no doubt we will be covering off on AI and robotics again. So thank you to our panel. If you don't mind hanging on for the audience there, thank you so much for joining us today. And I'm just going to make sure, just on the closing slide. So thank you very much for attending. We'll be closing off this session, and we're going to be joined today at 7 o'clock tonight, Australian Eastern Standard Daylight Saving Time, with Paul Williams from the UK, and he's with Black Arrow Space Technologies, and he's going to be looking at the net zero space flight. We have had Paul previously on our MySecurity TV channel. So this will be a good one, and having a look at what Black Arrow Space Technologies is doing. So join us again at 7 o'clock today. Thank you so much. Thank you to our panel, and I'll let you go. Enjoy the rest of your day.
Thanks.
Thanks, Chris. Yeah.
Thank you very much. Thanks, Navinda. Thanks,
Bye-bye.
Bilal.
Thanks everyone.
Ali.
Good to meet you all.
Thank you.
Cheers.
Thanks.
Thanks, Benjamin.